Hey guys, welcome to Unit 10 and our exploration of trigonometry. Today we're going to start off by looking at the three trigonometric ratios. Now remember, a ratio is simply a comparison of two numbers. And when we take a trigonometric ratio, what we're looking at is the comparison of two sides of a right triangle. So in our little exploration down below here, we have a right triangle with an angle of 35 degrees. Across from that, we have the opposite leg of that right triangle. Next to that, we have the adjacent leg, and then obviously the hypotenuse, which is always across from the 90. Now we have three trigonometric ratios, sine, cosine, and tangent, and they compare different sides of a right triangle. The sine ratio compares the opposite leg and the hypotenuse. So if I show you here by clicking on the sine ratio, its true meaning, it's going to take the measurement of the opposite leg and compare it to the length of the hypotenuse. So you can see here for a 35-degree angle that we have an opposite leg over hypotenuse equal to about 0.574. Now if I grab this little point here on my right triangle and I extend that, I'm not changing my angle, but I am changing the length of those sides. Notice that they continue to stay in that same ratio. All right, now let's take a look at the meaning of the cosine. The cosine ratio compares the adjacent leg and the hypotenuse. So here we go, let's swing our adjacent leg up and compare it to our hypotenuse. You see that for this 35-degree angle, the adjacent leg is about 0.818 in length compared to the hypotenuse. And again, as I drag and change the length of my adjacent leg and my hypotenuse, that ratio continues to stay the same no matter the size of my triangle. All right, one last comparison, the tangent ratio. The tangent ratio compares the opposite leg and the adjacent leg. So here we go, let's swing our opposite leg down and compare it to our adjacent leg. And we say for a 35-degree angle, the opposite leg is about 0.7 the length of the adjacent leg. And again, as I increase the size of my right triangle, I'm not changing my angle at all. However, the ratio stays the same. All right, let's jump into today's notes here. And have your graphing calculator ready for doing a little trigonometric calculation. So as we just discovered here, our three basic trig ratios go sine. It compares the opposite leg of the triangle to the hypotenuse. The cosine compares the adjacent leg to the hypotenuse. And the tangent compares the opposite leg to the adjacent leg. All right, now an angle of elevation is going to be used in today's lesson here. Our angle of elevation is always the angle formed between the horizontal line of sight and the line of sight to an object above that horizontal. Well, as you may guess here, the angle of depression then would be the angle formed between the horizontal and an object below that horizontal. So we have two different angles here of measurement, angle of elevation to above and angle of depression down to below. Also remember back to geometry when we studied special right triangles. We had two special right triangles based off of the relationship of their sides and their angle measures. So in our first one, a 45, 45, 90 right triangle, we said that you could set up this special relationship. Across from the 45-degree angles, you had two sides that were equal in measure. So we just call them x. Now, whatever the measure of those sides were, we would take that and multiply it by the square root of 2 to get the length of the hypotenuse. And likewise, in our 30, 60, 90 right triangle, we had these special relationships. Across from the 30-degree angle was the smallest side of our right triangle. We called that x. And whatever that was, we'd multiply that by the square root of 3 to get the length of the side across from the 60-degree angle. And finally, we would double the smallest side in order to get the hypotenuse. So the relationship of these sides are special, and that's what makes this a special right triangle. All right, let's jump into some examples for today. It says refer to the triangle at the right and give each ratio in terms of DC, BC, and DB. So if we take a look, here's our right triangle. BC is 12. BD, my hypotenuse, is 13. And DC here is 5.1. So if I want the sine of angle B, I'm going to start here at B, and I'm going to take the measurement of the opposite leg, which is 5.1, and divide it by my hypotenuse, which is 13. Likewise, for cosine B, I'm going to start here at the angle, and I'm going to take the measurement of the adjacent leg, which is 12, and divide that by my hypotenuse, which again is 13. All right, now for the tangent. Tangent of angle B, again, we'll start here at angle B. We'll take the measurement of the opposite leg of angle B, which is 5.1, and divide that by the adjacent leg of 12. Now, when we change angles here and go to angle D, we're going to take the opposite leg of angle D, which is now 12, and divide that by the adjacent leg, which is 5.1. Okay, go ahead and grab your graphing calculator here. For the next little section, we're going to take a look at calculating some of these sine, cosine, and tangents using our graphing calculator. All right, now the first thing to note is when you grab your graphing calculator, we need to go to our mode and make sure that our mode is set to degrees. So come down here to that third line, head over to degrees, and press enter. All right, now we're ready to calculate. So the first one asks us to just simply calculate the sine of 31 degrees. So sine, cosine, and tangent can be found right here in the middle of your graphing calculator. Tap on sine and enter in your degrees, press enter. So 0.515 is the measurement of that sine. So we'll write that down, 0.515. And what this means is that the opposite leg is just slightly over half the times the size of the hypotenuse. All right, let's try the next one now and go into the tangent of 89. So we tap on tangent, 89. We don't need to close our parentheses in this case, but we will, and we get 57.3. So what this means is that the opposite leg is 57.3 times the size of the adjacent leg. Remember, these are ratios, they compare two numbers. All right, finally, let's go to the cosine of 5. We'll tap in cosine, 5, hit enter, and we get 0.996. So again, 0.996 is really close to 1. And this should make sense. If you had a very small angle here of 5 degrees, let's say that's our 5 degrees, this adjacent leg here would be almost the same length as that hypotenuse. So it means the adjacent leg is 0.996 times the size of the hypotenuse. Now, we can use these facts here to help us solve some problems. So let's jump into a few more examples, keeping your calculator handy. We want to use the information in the diagram to find the measure of side PQ. So I'm going to highlight PQ here. Notice that this is a right triangle. We're given two sides, QR, and the hypotenuse here of 65, and this angle measure of 57.4. So first we want to use the sine ratio. Now remember, the sine ratio follows this so. So it's always the sine of the angle is equal to the opposite leg over the hypotenuse. So I'm going to start off by saying the sine then of 57.4 degrees should be equal to the ratio of my opposite leg, which I don't know, that's going to be side PQ, over the hypotenuse, which is 65. Now what I have here is sine 57.4 is just a number. So I have a number set equal to a variable being divided by another number. Well, we need to solve for x, so we need to get this number out of the denominator, and we're going to do that by multiplication. What we do to one side, we have to do to the other. So I'm going to multiply both sides here by 65. All right, so let's go back to our calculator now, and we'll end up typing in here 65 times the sine of our angle, which is 57.4 degrees. Close our parentheses up and press enter, and we get 54.76. So PQ is equal to 57.76. Yes, nope, just kidding, 54.76. We'll change that. All right, now let's try part B. It says to use the tangent function. Well, again, tangent follows this ratio of TOA. In other words, it's the tangent of the angle, 57.4, is equal to the relationship between the opposite leg, which again we don't know, so we'll call this PQ, or x, over the adjacent leg, which now is 35. So again, we have a number set equal to a variable divided by a number. We need to get that variable by itself, so we're going to multiply both sides by 35. And now, back to our graphing calculator, we'll have 35 times the tangent of 57.4. And that's going to give us now, again, it should be very, very close. There might be a little bit of error in there just based off the rounding. But you see that we get PQ is equal to 54.73. All right, finally, one more method to solve this is using the Pythagorean theorem. So remember back to geometry, Pythagorean theorem ruled a squared plus b squared equals c squared. Anytime we have a right triangle, it's the square of the, it's the sum of the square of the two legs added up equals the square of the hypotenuse. So let's substitute in what we know. We got 35 squared plus b squared is equal to 65 squared. Now I'm going to solve for b. So I got to get b squared by itself first. So we'll take 65 squared minus 35 squared. Now be careful. Don't assume that this is equal to 30 squared. You need to square first. Follow your order of operations. However, we're going to do this all in our calculator one swoop. So we're going to take the square root of both sides. So b should be equal to the square root of 65 squared minus 35 squared. So tap that into our calculator here. We got the square root of 65 squared minus 35 squared, and that's going to give us the length of 54.77. So once again, you see that all three measurements and techniques come out to give you a fairly close results. All right, let's try another example here. We got a hiker who's out in the forest. He stands 6 foot tall and 34 feet away from the base of a tree. So if I come back here 34 feet, let's say, and here's my 6 foot hiker who has this horizontal line of sight to the base of that tree, and it looks up at a 65-degree angle. So here's our angle of elevation. It's looking above that horizontal line to a point up there at the top. And we want to know the height of this tree here. So we want to know this vertical distance down to that horizontal line. And keep in mind, this will form a right angle. We have our adjacent measurement of 34, and we want to find our opposite measurement of x. So opposite and adjacent implies the TOA ratio, or the tangent ratio. So we'll set up the tangent of 65 should be equal to the opposite leg over the adjacent leg. Now again, we have our variable in the numerator. That means we're going to multiply both sides by 34. That gives us 34 times tangent of 65. And that's going to give us 72.9. So that means x here, 72.9, is this distance here from about the base of that tree all the way up to the tippy top. However, we also know that the line of sight here starts at about 6 feet. So we have to add in an additional 6 feet to get the total height of that tree, and that comes to about 78.9 feet. All right, one final example for today on special right triangles. We want to use these special right triangles here simply to write these ratios. So the sine of 30 degrees. So remember, our sine ratio is opposite over hypotenuse. So if we start here at 30, our opposite leg is x. Our hypotenuse is 2x. Now I can simplify this. Our x's cancel out. The sine of 30 is equal to 1/2. Cosine of 30 now is our adjacent leg over hypotenuse. So in this same triangle here, we have x root 3 over 2x. And again, my x's will cancel out, and I'm left with root 3 over 2. All right, sine of 45. Let's jump over here to our 45, 90. Remember, the sine is opposite over my hypotenuse. So that becomes x over x root 2. Now, again, keep in mind my x's will cancel out. That will be 1 over the square root of 2. However, you can't have a root 2 in the denominator. We need to rationalize that by timesing both the numerator and the denominator by the square root of 2. And that results in root 2 over 2, which is the cosine and the sine of 45 degrees.